All right, so we are now the day before the exam, exam one. So I do want to talk about what to expect and what you're going to see on it. Um, and just because I want you guys to be ready. So first things first, let me just go ahead and go to a whiteboard. I'm just going to sit here today instead of hopping up to my whiteboard. Let me clear all this stuff from earlier. So what we've got going on with this exam. So just like with the quizzes, they're going to be turning on at 1 o'clock. Okay, so the exam is going to be Friday, right? So it's going to start with 1 p.m. That's going to be when you can actually access it. It needs to be uploaded by 3:30, right? So basically the way to read this is I'm giving you the 2 hours for the exam, just as if we were in class. And I'm giving you an extra 30 minutes to deal with technological issues, all right? But this one, you must upload it in Canvas, all right? It's too much for me to have to deal with things when I'm getting emails and other stuff. So make sure you upload it in Canvas. Now I know most of you have not been having a problem with that. Like with quizzes, everything worked out just fine. But please make sure you upload in Canvas. So here's the deal. I don't want you starting to upload it around 3:30. You should start uploading it around 3. Okay, this isn't a 2.5 hour test. It's a 2 hour test with 30 minutes of upload time. So I will be on. I'll be on. I'll probably even be in our chat classroom if you need to pop in there if you have questions on it. So if you're starting to run into issues, right? It's like 3:10, you're trying to upload and it's not working. I don't want you to panic. I want you to get a hold of me and we'll get it worked out. But I really do need them uploaded into Canvas. Okay, so just realize it's meant to be a 2 hour test and the remaining time is to deal with uploading it. All right, so in terms of what it covers. All right, so it's going to cover chapter 2. I think. Is that the right chapter?
Chapter 3, I think.
Okay, chapter 3, thank you.
3.1 is vector value functions.
Okay, so it's going to cover chapter 3, which is all the vector value function stuff, and then 5.1 and 5.2. Okay, so what all that stuff is. So chapter 3 is your vector valued functions. Sorry about that.
All right, so no chapter 4, Bruce?
Correct. We are not doing chapter 4 at all. We skipped that. Chapter 4 is part of Math 107 in our sequence. So that's already prerequisite material. So we're not going over that. That would definitely be something to look at if you're not super familiar with multivariable stuff, because that's where we talk about things like partial derivatives and the like. But no chapter 4. So vector value functions, things to know what to do with them. Oh, I don't know, differentiate, integrate, limits, domain, yada, 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 right? So all of the things that we care about, regular functions, we want to know about with vector valued functions, which hopefully you recognize is the same thing, just more, right? We end up doing it once for each component or what have you, okay? So know the generals, just how to deal with them, all that. Actually, let me put one more on here. Let's talk about graphs. Excuse me. So know how to draw the graphs, which is basically graphing parametrics. But what we're really doing is we're graphing where the tip of the arrow is located. All right, so know how to operate with those. Now, some other things that chapter 3 has in there. Big T, big N. Know about unit tangent vectors, unit normal vectors, how to find them. I will expect that you know how to find these. Remember that it's a lot easier if we happen to be at a point, which actually just reminded me, once we're done with this, I'm going to go over the quiz. I know I haven't returned them all back. Some of you have them, but some don't. I'm going to finish those today, but I want to go over it just so you can see. This just reminded me that we had to find T and N on there. But anyway, so find big T and big N. So big T is a unit tangent vector, so length 1 pointing in the direction of travel. And then big N is the unit normal vector, the principal unit normal vector. It's also length 1. It is normal to the curve, so perpendicular to the curve, and it points inward towards the center of the osculating circle. Okay, so no big T and big N. Related to that are things like curvature. Be able to determine the curvature and what that tells you. So I'm also going to input osculating circle because that's related actually to both curvature and N. N points towards the center of it. And then the radius was just 1 over the curvature, right? So curvature can go from 0, meaning linear, to as big as you want as that thing gets tighter and tighter of a curve. So as it gets bigger, it's a smaller osculating circle. And then another thing that was related to big T and big N, I'm just going to put here physics, because we used these vector value functions and stuff to talk about a lot of stuff with physics. So in general, things to know about projectile motion. Let's just go with circular motion. Trying to think if there was a third one we talked about, but just in general, know how to deal with them as well. So I think I'll just kind of leave it like that. Well, we'll just put general down below. And then so related to this were the AT and the AN. So just remember that this is tangential acceleration. This one's normal acceleration. So centrally pointing, also known as centripetal. Right? And the tangential, this is the one that changes speed. And then this normal, this is the one that changes direction. So we usually have both. We usually have both of those components, but together they combine to form your acceleration. So like if we wanted to have a little formula that related those things, I would say here that A, it's equal to AT plus AN. So if I want the vectors, just so you know, I'll ask for the vectors or the components of your acceleration. So like if I ask for a tangential component, that's the entire vector AT. All right, the centripetal acceleration, that component is AN. If I don't want the vectors, I just want their sizes, I'll ask for the magnitude. Right, I'll say like, what is the magnitude of the centripetal acceleration? Then you just need to get the magnitude of this thing. You don't actually have to find AN, right? Because in the book, they wrote it like this. So you can think this is the magnitude of the tangential acceleration times the unit tangent vector, so it's pointing in the right direction. And then the same thing here. This is your component or your magnitude of the normal acceleration times the centrally pointing vector. And so it gets it. So we've got a whole bunch of formulas for all this stuff, but there are lots of ways to get there. All right, so Victor, you said, let's see, in the chat box, when acceleration is constant, there's zero normal acceleration. Okay, no, that's not necessarily true. I think maybe what you're saying is when the velocity is constant. Okay, so if velocity is constant, then there's no acceleration at all. Okay, because if velocity is not changing, then there's no acceleration. If speed is constant, then there's no tangential acceleration. If the direction of travel doesn't change, then there's no normal acceleration. So does that make more sense? Does that kind of answer your question? Yeah, okay, cool. Yeah, so like if we've got a particle that's moving in a line, but it's speeding up or slowing down, then there's tangential acceleration, but no normal acceleration. If we've got constant speed, but we're changing direction, then we have only normal acceleration. You get that in like uniform circular motion. But usually there's a combination. Usually your speed and your direction are changing, so you got both. All right. Yeah, so I think that's pretty much in a nutshell what's in chapter 3. Like it doesn't look that much when we just put it here, but there's a lot to it. And like I was saying before I answered Victor's question, that we do have a bunch of formulas for finding AT and AN, for finding curvature. Obviously, I'm not expecting that you memorize those. This exam is, I mean, it's open book, open note. Obviously, I can't police that. So feel free to use those resources to help you find the formulas you need to calculate these things. But the one thing that's not okay is to use some online resource, like to put in a vector value function and say, tell me the derivative, right? That's not okay. That's just the same as copying somebody else's work or, you know, and plagiarizing for a paper or something. So don't do that. You can use your tools to help you get where you're going, but do it yourself. Show me your own work. And that includes working with each other. Okay? Don't do that on exams. Right? Anyway, so there's chapter 3. Any questions about that kind of broad overview of chapter 3 before we talk about what's in 5.1 and 5.2?
I have 2 questions for you. First one is, are we using calculators or do you want exact values?
Okay. I would prefer exact values.
Okay.
Yeah, so I would prefer getting something like root 17 over 4 for your curvature, let's say, than, you know, whatever that decimal approximation would be, 1 point something, right? Okay. So, yeah, like you can use your calculator to help you get to there, but leave it as exact values, not as approximations. The only place that like I'd be okay with that is in one of these like applied problems, you know, where you're doing like the projectile motion and stuff like that. Like on the quiz, when we go and we look at the quiz, there was that one about, you know, how far away does that object land? That one I'm totally cool with getting a decimal for. Mostly because trying to solve for it exactly means solving a quadratic for time, which plugging that in is kind of a big old pain in the butt, right? So in an applied situation, like the physics stuff, yeah, you can give me decimals. But if we're in the mathy world, like I'm asking you to evaluate a limit or find a curvature or things like that, I want exact values. Okay, so that was the first one. You said you had a second question?
Yeah, could we go over osculating circles?
Yeah.
Like just one example.
Totally. All right, well, let me do this. I'm going to go ahead then and clear the whiteboard. I think we're all good with everything here so far, I hope. So let me just go ahead and clear this, and let's do an osculating circle kind of deal. All right, so for example, let's say, I don't want to make it super complicated. Yeah, let's do this. Let's do y equals x squared. And let's find the osculating circle at x equal 1. Or even better, since it's rectangular, let's just call it the point. All right, so that's our goal. So think about y equals x squared. We all know what it looks like. So at 1, 1, there is a sort of best fit circle. All right, so it looks something like that. So basically we're looking for where is that, what is that circle? All right, so is this kind of what you were talking about, Bradley?
Yeah.
All right. So here's where you should start. First things first, you should figure out the curvature. Because we know the radius of this circle is 1 over the curvature. So let's get the curvature. So does anybody remember a formula for finding curvature? Because we've got a bunch of them.
The magnitude of r prime cross r double prime divided by the magnitude of r prime cubed.
Okay. So we can definitely use that one. What that's going to require us to do is to create an r. Right? We need to actually make this as a function r of t equals. I'd rather not do that. So does anybody remember the way you can do it with rectangular? It would have been the last of the equations that we created for curvature.
Can you repeat that?
What's the formula for curvature when we have a rectangular equation?
It is
y magnitude of y double prime over the I got this. It's the the quantity to the third power of the quantity under the square root of 1 plus y prime squared. But on top, it's the magnitude of y double prime.
So square root of 1 plus
y prime squared. And then cube all that.
That's all cubed. And then you said it was the magnitude
of y double prime.
Y double prime. What do you guys think? Does that look right?
I don't think it should be magnitude of y prime inside the square root.
Yeah. I don't think it's in the square root either.
Well, I will tell you this. I know for sure you don't need magnitudes because these aren't vectors. However, we do definitely want absolute value because we need to make sure that this is positive, right? Curvature is a positive number. Okay.
Yeah. For the most part, like you said, absolute value of y double prime divided by the square root of 1 plus y prime squared. That's always going to be positive, so that doesn't matter.
Correct.
Cubed.
Yeah. So that was close. Was that you, Seamus, who gave me that?
Yeah.
Okay. Here's what's just a real quick aside. I think this is really funny is I recognize you guys by voice now. And so I don't know what most of you, well, no, some of you, I have no idea what you look like, but I know exactly what you sound like. So I think that's just kind of funny because that's the nature of the world we live in. But yeah, so this we just want absolute value of y double prime. And we don't really need the magnitude stuff there. But this is what we're going to use for sure. Right. But yes, as Caesar said, you could also think of it as to the 3/2 power, right? The square root. Anyway, so now that we've got that, let's go ahead and calculate this. So we've got y equals x squared. So y prime is 2x. Y double prime is 2. At our specific point, right, we're looking at 1, 1. Then y prime is equal to 2, and y prime double prime is also equal to 2. So we'll go ahead and put those in to calculate our curvature. So we get k is equal to 2 over the square root of 1 plus 2 squared cubed, which is 2 over 5 to the 3/2. And I'm just going to leave that as it is right now. So there's our curvature, which then means that the radius of the circle is this thing flipped over. It's 1 over that. So it's 5√5 over 2. So this circle, this osculating circle, this best fit circle, when we're out at 1, 1, has a radius of 5√5 over 2. All right, so far so good?
Yep.
At least once we settled on what the curvature formula was. Okay, so now if we want to find the equation of the circle, we need to know where the center is. We've got our radius. If we can just find our center, then we're good to go. Okay, so here's how we're going to do that. We need n, because if we go back to the picture, right, we know that n is pointing towards the center, right? T is tangent to the curve, but n is pointing towards the center. So if we can find n, then we can go this distance, this radius distance, to get to that point. So that's the next thing we have to find. So if I'm ever doing an osculating circle thing, I start with k so that I get my radius. Then I go and I find n. All right, so let's go find n. So ideas, thoughts, suggestions? What are we going to do to find n?
Find big T.
Yeah.
Okay, so if we know big T, we can use that to find big N.
Flip and make one negative.
Okay, so how are we going to find big T? Oh, and I definitely like that idea of let's flip, switch the coordinates and make one negative. Since we're in the 2D world, we can definitely make use of that.
What
Okay.
we need to parameterize y equals x squared, though.
All right, so we can do that to get our R, right? So like R, we could think of it as T comma T squared. I just let X equal T. And then I can use that to find big T. So in a pinch, you can always parameterize, just let X equal T. However, I'm not going to do that. Let me just show you what happens if we do that. If we go to R prime, that gives us 1 comma 2t. And at our point, we get then that R prime is equal to 1, 2. Right? Because if X is equal to 1, that means T is equal to 1, which makes that guy 2. Okay, so we could have done this, which then means if we want to find t, we just have to divide by the magnitude and we're good, right? So t would be 1 over root 5, comma 2 over root 5. So you like how I said I'm not going to do it that way, and I just did it that way. So, but that definitely works. But you can do this a little bit faster because I want you to check this out. If we have y equals x squared, remember what the derivative was?
2x.
Y equals 2x. Well, that is that guy. So if you ever want to get, say, r prime, it's always going to be 1 comma the slope, 1 comma the derivative. So I could have jumped straight to going with the, okay, so then r prime is going to be 1 comma y prime. So it's going to be 1 comma 2x, which is 1, 2. And since I already did this, since I already calculated y prime, I might as well make use of it instead of kind of starting from scratch. So this is my recommendation if you're in rectangular and you're in the plane. But if you don't see that, that's fine. You can still build it. All right. Well, anyways, this leads to the same t of 1 over root 5 comma 2 over root 5. All right. So that's awesome. We got our t. So now the question is, what is n? Okay, well, let's use what we know about it. We know that n is going to be, well, if we swap these, right, we just swap them. But now we have to make one of them negative. So which one are we going to make negative, the x or the y?
The x.
Okay, why?
Well, if I think about normal, if I, you know how you drew endpoints.
I like the joke, Bruce.
Yeah, thank you. I'm glad somebody got that. That was a total dad joke. Get it? X, Y. Sorry. But yes, I agree. You know, Victor also put in the chat box the direction, right? If we look at that picture, like you were saying, Bradley, we know that n, because we know about this parabola, we know where it is. We know n has to be pointing up and to the left. Well, up means a positive y, but left means a negative x. And you would have found this, you totally would have found this if we had gone through and found t as a function and then did the whole differentiate it and divide by its magnitude, right? Like if we come back over here, before plugging in 1, 1, we would have found that t was equal to 1 over the square root of 1 plus 4t squared, and then 2t over the square root of 1 plus 4t squared, right? I'm dividing by the magnitude of r prime. And then this, if we had differentiated and divided by its magnitude, would have led to something that when we plugged in 1 would have given us negative 2 over root 5 and 1 over root 5. But this is a great example to show why we don't do that, right? Let's use what we already know. I'm convinced that one of the ways that you get to be a good mathematician, or to be a good mathematician, one, you have to have a good memory, right? Like there's tons of stuff that we have to remember. But two, you have to be really observant. You have to be able to see when you've got information and use the information that you already developed. It's being efficient for sure, but you know, you have to be able to recognize, oh man, I already know a lot about n. How about I use that? Or I'm in 2D. Well, cool. I know how to get a dot product so that it's 0. I can just, you know. So anyway, pay attention to stuff. Remember stuff. As you're going, realize that sometimes in the middle of a problem, you run into something that you're going to be able to use later. Don't reinvent the wheel, right? All right. Well, anyway, so there's our n. We feel okay with that? I hope.
Yeah.
All right. So now to go find our center, what we need to do is we're going to use that n, and we're going to use this radius. And so we know that the center is actually going to be 1, 1 plus, and I've got that 1, 1 because that's where our point was, right? We started at 1, 1. But now I need to go in the direction of n times my radius. So it's going to be 5 root 5 over 2 times minus 2 over root 5, comma, 1 over root 5. So Victor, just, yeah, that was perfect. You put that in the chat box. He typed r times n plus the starting point, right? So there's my r times n plus my starting point. So let's see what that gives us. So this one, the 2's cancel, the root 5's cancel, so I get minus 5. 1 minus 5 is minus 4. For the second one, the root 5's cancel, so I get 5 halves plus 1, I believe is 7 halves. So there's the center of my circle. And now that I've got the center of my circle, I can go ahead and get the equation of my circle. So I'm just going to write it up here. So we're going to have x plus 4 squared plus y minus 7 halves squared equals, what is that, 125 fourths, I believe, when I square the 5 root 5 over 2. Whew. All right, so there you go. There's
Nice.
the equation of the osculating circle. Well, think about this. I put one of these on the test, and look at everything I'm testing you on. I mean, talk about like a problem that's chock full of stuff. It's got curvature, it's got n and t, it's got being able to move in the direction of vectors a certain distance. I mean, well, in addition to remembering stuff about circles and whatnot. But this has a ton, which I want to bring up again. Remember how Seamus asked me how many questions were going to be on the test, and I was like, oh, it doesn't really matter. This is why it doesn't really matter, right? Because I can give you one question that tests you on like half of the stuff from this chapter. Or I give you 3 questions that test you one of each of the 3 different concepts, right? And it shouldn't change how you study because you still need to be able to know how to do all of them. But that's just my personal opinion, and I'm not the one taking the test. So anyway. All right, so is that good, Bradley? Seeing you were the one that asked about that, you feel good about that example?
Yeah, it was awesome. Thank you.
All right, cool. Okay, so then, so chapter 3. This problem was actually a good representative of, like I said, about half of chapter 3. You know how I could even make this cover more of chapter 3? Like, it'd be really easy. I could do something like, there's a particle traveling on this path. So not only do I want to find, say, the osculating circle, I also want to find the tangential and normal accelerations. Boom, there's that much more from chapter 3. I could also, instead of giving it to you in rectangular, or I could give it in rectangular and say, turn it into a vector valued function. Find its derivative, its integral, right? Like this one question, I could get to cover just about everything from chapter 3 if I felt so inclined. So how about a 2-question exam? What do you guys think? One question that covers chapter 3 and one that covers chapter 5?
I'm down.
I'm not.
I would
down.
be down, except no, yeah, because if we can't get one of those problems, we're boned on that.
That's kind of where I think too. Yeah, if I give you something like this and it starts going awry, you're toastage. But yeah, no, I could give this to you. We could easily have a 2-question exam. That sounds a little frightening even to me. So.
It still confuses me a bit, especially the center part.
All right. What can I do to help you see what we did? Like, let's break it down a little, Jordan. So the 1-1, are you okay with where that's coming from?
Yes.
Okay. So, because we always want to go from the point where we're starting.
And the
Okay.
5 square root 5 over 2.
You're good with that because that's our radius. That's how far away we want to go. So
And I know that that's the n.
so we're multiplying it to n because n points in the direction we want to go, right? N points towards the center. So we're going to use this vector to move us in the right way, the right direction. We multiply it by r so that it's got the right length because n is length 1, right? That's why they're called unit vectors, right? So the unit normal vector, it's length 1. By multiplying it by the length of the radius, that vector now is as long as the radius, which means, like, if this was our n, my picture doesn't really allow me to extend it much, but so I multiply n by my radius. So now it's a little bit longer, but that point out at the end, that's the center of the circle because this vector has the right length and it's pointing in the right direction. So that's why we do this. The r times n makes it so that what we're adding is the length of the radius in the right direction, and we add that to where we started. So it's always that, always that. You take your starting point and you add to it r times big N.
Okay.
Does that make a little more sense?
Yeah.
I don't know that I believe that, yeah, but I'll take it as a,
Yeah, I'm getting that bit at least.
okay. All right, so cool. So that was a very good question to ask, Bradley, because it did bring up lots of things. So bonus points there.
I have a quick question about this circle.
Sure.
That radius is kind of big.
Yeah.
Is
I mean,
that
I
okay?
guess. What do you mean, is that okay?
Like, is this circle supposed to fit inside the function y equals x squared?
Not necessarily.
Okay.
Yeah, because sometimes they do expand out beyond other parts of the curve. Think about when you did tangent lines. There were plenty of times that a tangent line would then intersect a curve later, but locally it fit. It's
Okay.
exactly the same idea here, that this circle locally fits, but does it spill out over the other one? Possibly. It's not as big as you might think, because 5 root 5, that's the square root of 125, which is like 11, a little more than 11. So you divide by 2, it's like 5.5, 5.6. So it's not really that big, but it definitely does spill over onto the other side, I think.
Bruce, could we go over the quiz? Because I haven't gotten my grade back.
Yep, I definitely am going to do that.
Thanks.
Yeah, that's still on my plan. But before we do that, let me really quickly talk about what to expect from chapter 5, right? Because we had a couple more sections there. So from 5.1 and 5.2, this is basically double integrals. No polar. Okay, we just started talking about that last time. We haven't talked about it enough. That's not going to be on the exam. So I need to check and see if that homework's actually due Monday night. If it is, I'll bump it back. But it's just going to be double integrals. So things that you should be able to do, right? Evaluate them. If I give you a double integral, you should be able to do it. You should also be able to set them up. So if I give you a region, you should be able to set it up. And what I'm going to put here is both ways, meaning dy dx and dx dy, right? Make it so the integration man is sideways, make it so he's vertical, be able to do it both ways. So you should be able to set one up given a region, be able to do it both ways. You should also, with this whole both ways thing, be able to switch the order. Sometimes it's useful. Sometimes it's necessary. All right. So this bit from double integral should be fairly straightforward, nothing really crazy. In terms of applications, just remember that the big application that we have so far is volume. So like if I ask you for the volume under a shape or under a surface, that's going to be doing a double integral. You do the double integral of that thing over the given region. Okay, so that will definitely be on there and probably be one of the easier parts, I think, of this exam, especially like the evaluate. Like if I just give you a double integral and say, hey, what is this number? You should be able to do it.
Bruce, correct me if I'm wrong, but a double integral is always a volume?
Not always a volume. Volume, it's a volume of if your surface is above the xy plane, and it's the volume underneath it. Just like a single integral isn't always area. Like if your graph that goes below the x-axis, it gave you the negative of the area. This can actually give you the negative of the volume.
Okay, I understand.
So then Victor also said, does this include general regions? And Matthew, thanks for throwing that in. Yeah, 5.2 is over general regions. 5.1 was over like rectangular regions. 5.2 makes it so that we can have crazier regions. But yes, I definitely mean those as well. All right, so any other questions about 5.2 before I jump to the quiz? No? Okay. So
I feel good.
Okay, so let me go over to the quiz real fast. And like I said, some of you have gotten it back, some of you haven't. I'll get those graded up here real soon. But basically, let's just go ahead and go over this. So for the first one, this was a projectile motion problem. I told you that we've got this ball that's traveling at 140 meters per second at an angle of 55 degrees. It's being launched from a height of 8 meters. And the question was, how far away does it land? All right, so in order to do this, we're going to use vector valued functions. And since it's projectile motion, we can do the same ones that we always do. So basically what I've got is a v of 0. It's going to be 140 times the cosine of 55, and then 140 times the sine of 55. That's always how this works. It's always the magnitude, so the speed, times either the cosine or the sine of the direction, and the cosines for the x and the sines for the y. So that's always the same. The height of 8 meters tells me that I can use 0, 8 as my initial position vector. Basically, I'm setting 0 to be the point underneath the ball when it's launched. So to answer this question, I started by creating my R. And so R, it's going to be a combination of, the first one's going to be negative 4.9 t squared. That comes from our acceleration. Since we're in metric, acceleration is 9.8 meters per second squared. And then I'm going to add to that my initial velocity times t. And then I'm going to add to that my initial position. So I can compose all those together. And this is my vector valued function that describes the position of this particle at any given time. Okay, so now if we want to know how far away it lands, what we know about that is that this is y equals 0, right? When it hits the ground, we're back at y equals 0. So what we're going to do is we're going to take negative 4.9 t squared plus 140 sine of 55 times t plus 8, and we're going to set it equal to 0. And we're going to solve this. If we go back, remember that Bradley asked me that question about do I want exact values or decimal approximations. This is one where I'm totally fine with you getting me a decimal approximation. Okay, so use your calculator. You get a couple of t values. I don't have it handy. One of them's negative, so you don't use that because it didn't hit the ground before you threw it. But whatever you get for that t, I don't remember what it was, so I'm just going to call it smiley face for right now. If we want to know how far away we go or we land, we just take that t value and we fire it in here to our x. So our x is going to be 140 cosine of 55 times smiley face. Not supposed to be a smiley face. All right, so whatever that number was, we multiply it by 140 cosine 55. So for this quiz, that's what I wanted you to do. All right, so there's that guy. Number 2 was finding curvature. And now that we kind of talked over finding curvature for that osculating circle, this will be really fast because finding curvature is just the beginning of it. So let me just erase this real quick. All right, so for the second one, you were given an r equals, and so we had r equals t cubed t squared, and I wanted you to find curvature. All right, so I went to r prime, that's 1 3t squared 2t. And then I got my r double prime, which is 0, 6t, and 2. And now you need to go to the curvature formula. I would use the curvature formula that involves the r primes and stuff like that. So for this one, the curvature is r prime cross r double prime, its magnitude, divided by the magnitude of r prime cubed. Well, that should be r prime, not r double prime. Hold on a second. Let me just erase this. So that's one of the other curvature formulas. But since this one we know we're looking at the origin, let's plug in those values. So 0's in for t. So r prime is going to be 1 0 0. R double prime is going to be 0 0 2. So the magnitude of r prime is 1. If we do r prime cross r double prime, I'll let you do this on your own. You get 0 minus 2 0. So its magnitude is 2. So that makes our curvature 2 over 1 cubed, which is 2. So that's the curvature of that thing at the origin. All right, so good for that one. All right, sounds like we're good. All right, so let me go ahead and clear this real quick. Oh no, just erase this side. We'll keep these in half at a time. Okay, so then question number 3. For this one, I wanted you to find a normal and tangential acceleration components for a particle that was moving on a given path. All right. So for this one, the path was t squared, t cubed. And I wanted you to find these guys, the AT, the AN, when we were at -1, -1, 1. Or sorry, 1, 1, -1. So again, our R is t squared, t cubed. But again, we're at 1, 1, -1. So this actually tells me that that's t equal -1. So I'm going to use that here. So R prime is 2t, 2t, 3t squared. Right, so that's also, think of that, that's V. So then A is our double prime, which is 2, 2, 6t. And so at my specific point, V is -2, -2, 3. And A is 2, 2, -6. All right, so let's go get the components. So AT, the magnitude of it, is V dot A over the magnitude of V. So V dot A, that's -4, -4, -18. And so that's what, -26, I think. And then the magnitude of V is the square root of 4 + 4 + 9, which is the square root of 17. So we got -26 over the square root of 17. Okay, so that tells me then that the tangential component is this times my V. So that's going to be 52 over root 17, 52 over root 17, minus 78 over root 17. So we're halfway there. That's our AT. Now, to get AN, I'm not going to bother finding N. I'm just going to use the fact that AN is equal to A minus AT. So I can just take 2, 2 minus 6 and subtract from it this guy. Anyway, so I'm not going to bother because we're running out of time. I'm not going to bother doing that, but that's how we would figure out the normal component. So this is definitely a recommendation I have for you if you're ever going to try to find the normal acceleration. Find the tangential first and then just subtract it from A. It makes things a lot easier. And if you're ever at a specific point, go to that point first. Okay, so good for that one. All right, so the last one, I wanted you to set up an integral to find the arc length parameter. It didn't actually make you go and do the whole thing because it's a little much. And this is actually something you should probably put on your list from chapter 3. I forgot to mention it. The arc length parameter R, right? But this is basically the way that we can convert from having our location in terms of time to having our location in terms of distance, right? That's kind of the whole point of that one. So let's go ahead and get this guy set up here. So the R we had was cosine t plus t, sine t minus t, and t. So if we want to get arc length, our S, it's the integral from 0 to t, which means we're going to have to put in a dummy variable. But here we need to have, it's the magnitude of r prime. So we're going to have the square root of minus sine of t. Oh, shoot. I just said we needed a dummy variable, and I went ahead and I wrote t. So minus sine of u plus 1 squared plus cosine of u minus 1 squared plus 1 squared du. So that's all I needed for this one, was just that. Depending upon what these functions are, these can get gnarly. But this then would get us a relationship between s and t. And so we could change our parameterization in terms of s, which sometimes has use. Anyway, so there's the quiz. And again, I apologize, not everybody's got them back, but they will be there shortly with your scores. All right, so I'm gonna quit sharing my screen so we can kind of wrap this sucker up. Oops. Pressed the wrong button. All right. Okay, so I think you know what's coming. Like I said, it will be available starting at 1 o'clock. Just make sure you get it in by 3:30. I will be on, so if any questions pop up in the middle, go ahead and come to this Zoom session, and I will help you out. I also have office hours tomorrow from 10 to 12, so feel free to pop in there if you have any questions. All right. So with that, I'm going to pause our recording.